In the last couple of sections, when we've been talking about linear functions, we've concentrated mostly on the idea of the slope as a rate of change. In this section, we're going to concentrate a bit more on the geometry of slope here in section 2.4. We've already seen that whether our function is increasing, that is, having a positive slope, or decreasing, having a negative slope, these particular words actually specify very specific math concepts. We'll talk about that whole idea of increasing and decreasing throughout the course, but I'm going to start using those words a little bit in this section as we label some of our graphs. How fast our function is changing, the rate of change, is visible geometrically on the graph as the steepness of the graph. Right? The steeper the graph, the faster the y value is going up, and therefore the faster the rate of change. The larger the absolute value of the slope, therefore the faster the rate of change. The reason that I said absolute value here is when I'm thinking about how fast something changes, it can change very fast in the positive direction, or it could change very fast in the negative direction. So I don't want to think about positive, negative. I just want to think about how big that slope is to determine how fast it's changing. In example 1, we have graphs of several linear functions, and we're going to label each one using these words, increasing or decreasing, and then we're going to match with a description at the bottom of the page. So as I look at the first one, this definitely is going uphill. We always read graphs from left to right. So it's going uphill or increasing. B is going downhill or decreasing. C is again going downhill or decreasing. And D is going back uphill, so this one is increasing. Again, those words increasing and decreasing, you always want to think left to right when you use them. All right, so let's match each of these descriptions. First, I have a large and a small positive slope. The positive slopes are going to be the increasing graphs. So for starters, since these are both positive slopes, I know I'm talking about A, a positive slope or increasing, or D, a positive slope or increasing. Now compare them. This line goes up a lot faster than that one. So this has a larger rate of change or a larger slope here in D, whereas this one doesn't go up nearly as fast. It's got a smaller rate of change. It's going to have a smaller positive slope. All right, the other two, the decreasing ones. The negative slopes are going to have decreasing graphs. And notice again, this one's going down a lot faster, a much larger rate of change, just in the negative direction. So C here is going to have a large negative slope, while B still is decreasing. It still has a negative slope, but not nearly as fast. So it has a small negative slope. There are a couple of special slope situations that we haven't discussed yet. The first one has to do with horizontal lines. This graph's sort of a general horizontal line here. It goes both ways forever. And I'm asking the question, first of all, is a horizontal line the graph of a function? Well, yes. Certainly passes the vertical line test, right? No matter where I draw a vertical line, it's only going to hit that graph once. So we can then ask the question, what's the slope of a horizontal line? Well, one way to think about slope is rise over run. Let's think about that for this graph. To go, say, from this point to this one, I'm going over 2, but I'm actually not going up at all, right? My up is like a plus 0. So rise over run would be 0 divided by 2, which is still 0. The slope of a horizontal line is 0. Does that make sense when you think about your concept of slope as steepness, right? Over on this page we're talking about the slope as the steepness of these lines. A horizontal line is not steep at all, right? Either in the positive or negative direction. It has no steepness. There's 0 steepness. Completely flat. Well, since we do have a numerical value for m at 0, we could find the equation of a horizontal line using kind of our normal linear equation, y equals mx plus b. M is 0, and 0 times x is still 0, so I just get y equal b. Our equation will not have an x in it at all. It will just be y equal to whatever the y-intercept is. I could write that in function notation as f of x equals b. And if you remember back, it's been a couple sections now, we called that kind of function that didn't have any x's in it at all a constant function. Hopefully that makes sense, right? The y value is just constant. In this case, it happens to be whatever c is. The y value is just constant all the way across that line. So, on a horizontal line, all the y values are the same. The slope of a horizontal line is 0. And the equation is y equals b. Horizontal lines are graphs of constant functions. And the function is neither increasing nor decreasing. It is constant. And therefore, if I was using it like in real life to model a quantity, it would have to be modeling a quantity that does not change. And certainly there are things in the world that don't change. For example, the height of a person. Once a person's full grown, their height doesn't change. We'd have to model that with a constant function. So these things do have realistic applications. So slope of 0, and the equation is just y equals whatever the y-intercept is. All right, the other type of slope that we haven't talked about yet would be slopes of vertical lines. So here's a vertical line again, goes up and down forever. And the first question, is a vertical line the graph of a function? Well, does it pass the vertical line test? It fails it about as spectacularly as it possibly could, right? This vertical line certainly does not hit just one point on the graph. It hits infinitely many points. So this is absolutely not a function. It fails the vertical line test. What can we say about the slope of a vertical line? Let's think about rise over run again. If I go from one point to the other, I'm going to pick those 2 points. I'm going up 3, but I'm not going left or right at all. so I'm going over 0. So rise of 3, run of 0. You can't divide by 0 though, right? Division by 0 is undefined. So the slope of a vertical line is undefined. Since I don't have a numerical value for m, I'm not going to be able to use this equation because I don't have any number to plug in here for m. So I'm going to have to come up with a different way to find the equation of a vertical line. And I'm going to suggest that we go back to the graph here and just think for a minute about all these points. This point was labeled the C0, but let's label a few more points on this graph. This point would be C3. That point would be C-2. And this one would be C-4. So although the y values change, all of the x values on a vertical line are identical. And for that reason, the equation of a vertical line is just x equals whatever that constant value is. So quick comparison. On a horizontal line, all the y values are the same, and the equation is y equals some constant. With a vertical line, all the x values are the same, and the equation is x equals whatever constant. So quick summary, on a vertical line, all the x values are the same. The slope of a vertical line is undefined. And the equation of a vertical line is x equals some constant. We think about using vertical lines in modeling. Vertical lines are mathematically kind of interesting things, but they're not especially useful because most often when you think about something changing over time, things can't change as no time passes, right? It doesn't make sense to say, hey, at a certain time, something has all kinds of different values. So vertical lines are much more rare in applications than horizontal ones are. All right, let's practice that just a little bit. On the next page, we're going to write the equations of a few horizontal and vertical lines. All right, first graph here, my vertical line. All of the x values are the same. No matter what point I pick on this line, the x value is always -1. So the equation of that line is x equals -1. Next example, I have a horizontal line, and notice no matter what point you pick, all of those points have the same y value. The y value is always 2. Take a moment and write down the equations of these last two lines. All right, and hopefully you decided on y equals -4. Horizontal line has all the same y values. And then x equals 3. This vertical line has all the same x values. All right, one more geometric idea with our lines. I want to talk a little bit about parallel and perpendicular lines. Parallel lines never meet, and it will always be true that parallel lines have the same slope. Why does that make sense? Well, remember, slope describes the steepness, the rate of change or steepness of the line. And parallel lines have the exact same steepness, right? So they have to have the same slope. So if I've got two lines here, these slopes must be the same. In other words, M1 has to equal M2 because the lines are parallel. What about perpendicular lines? Perpendicular lines have slopes that are opposite reciprocals of one another. Let's unpack that just a little bit. I've got my two perpendicular lines, right? They meet at a 90-degree angle, so they're perpendicular. Would you agree with me that if one has a positive slope, the perpendicular line is going to have a negative slope? So that's the opposite part. The slopes of perpendicular lines are always opposite signs. One will be positive, the other will be negative. What about the reciprocals? Well, the steeper this one is, the less steep that one's going to be. That's the reciprocal part of the slope relationship. Let's write this one in symbols. My first line has a slope of M1. My second line has a slope of M2. M2 is going to be the opposite, so negative, reciprocal, 1 over M1. So opposite, reciprocal. All right, just to practice those relationships a little bit, let's fill in this little chart. If I start with a line with slope 4, the parallel line will have the same slope, 4. But the perpendicular line will have a slope that's opposite, so negative, and the reciprocal of 4 would be 1/4. Try it again. My original line has slope -2/5. The parallel line will have the exact same slope, -2/5. The perpendicular line, the slope will be opposite. This one was negative, so this one's going to be positive. And then the reciprocal, 5/2. So that's generally speaking how you deal with parallel and perpendicular slopes. These last two are our special cases, the ones we just finished talking about. If the slope of my original line is 0, this is that horizontal line, right? Then the parallel line will have the same slope, 0. But what about the perpendicular line? I can't take the reciprocal of 0. 1/0 is undefined. So in fact, the slope of the perpendicular line is undefined. And that makes sense, because what's perpendicular to a horizontal line? A vertical line, right? With an undefined slope. This last line just goes the exact opposite direction. Excuse me. Erase that. The last line has the original slope is 1, so the parallel line will have the same slope, 1. The perpendicular line has the opposite, so negative, and the reciprocal of 1 is 1/1, or still 1. All right, we're going to finish up this section with a couple of problems finding equations of parallel and perpendicular lines. I want to find the equation of the line described in each example, and then we're going to check and see if we did it right by graphing and seeing if they look parallel or perpendicular. And there's a little hint here about the square grid. We'll talk about that when we get to it. So first of all, I want the equation of the line that goes through the point 0, 5 and is parallel to this line. So let's see. I know eventually I want y equals mx plus b. So that means I need to figure out the m and I need to figure out the b. All right, to find m, because the line I want is parallel to this one, I know it's going to have the same slope as 3x minus 4y equals 12. But what's the slope of that line? Well, that'd be a lot easier question to answer if I had it in that form, right? So let me go ahead and solve for y. I want to get y by itself, so it looks like that. So let's see. I'm going to start by subtracting the 3x. I have negative 4y equals negative 3x plus 12. Then I'm going to have to divide by negative 4 on both sides. And now I've got y by itself, which is what I was looking for. Negative 3 divided by negative 4 is positive 3/4 times x. And then 12 divided by negative 4 would give me a minus 3. In this form, I can now identify my slope. It's 3/4, right? Oops, smeared my pen a little bit, sorry. 3/4. And since I'm going to have the same slope, I will still use for my line the slope of 3/4. All right. Next, I need to find the b. Well, first of all, don't get distracted. It's not negative 3. That's the original line, not my parallel line. I need to find the b for my line. In this case, I kind of got lucky. Do you see that they gave it to me? They gave me the point 0.05. When x is 0, y equals 5 is the y-intercept. So b is 5. So if I put those two pieces of information together, my line is y equals 3/4 x plus 5. All right. Oh, rats, I didn't get my screen size exactly right for Desmos here, but we'll do our best. Let's go ahead and take a quick look at Desmos. And I realize you can't see the whole thing, but I'm going to do my very best here to make this work for you. Let's see if I do that. Maybe that'll help a little bit. There. All right. So what I'm going to do is I'm going to graph the original line they gave me, and I'm also going to graph the line that we came up with. And we're hopefully going to see that the two lines are parallel. So they gave us the line 3x minus 4y equals 12. So there's the original given line for this problem. Our new line was y equals 3/4 x plus 5. First of all, can you visually see that those two lines are parallel? They certainly look parallel. And notice my line, the one in black, does have the y-intercept of 0.5, just like we expected it to have. So it looks like we did do the problem correctly, and Desmos was a nice way to check that. All right, I've got one more problem here. In example 4, we'd like to find the equation of the line through the point -1, 2 that is also perpendicular to y equals 1/3 x plus 4. So again, I want to find the equation of the line, so I'm looking for y equals mx plus b, meaning I have to find an m and I have to find a b. All right, this time I'm looking at perpendicular. So I know that my slope has to be the opposite reciprocal of the slope of that line. All right, well this time they were nice enough to give this problem to me in slope-intercept form. So I can actually pick the slope out right here. I want the opposite reciprocal of 1/3. So the slope that I want is -3/1, or in other words, just -3. Right? I didn't have to do quite as much work as I did up here. Up here they didn't give me the equation solved for y, so I had to do that myself. Down here they were nice enough to give me the equation solved for y, so I could pick out the slope without doing any extra work, and then just took the opposite reciprocal for the perpendicular. All right, I also need to find b. This time they weren't quite as nice, right? Last time they gave me the y-intercept. This time they didn't. They gave me the point -1, 2, which is not the y-intercept. So I'm going to go back to y equals mx plus b, and I'm going to plug in some information. I've got an x and a y, and I've got an m. If I plug all those numbers into my equation, b will be the only unknown, and I'll be able to solve for it. So y is 2, m is -3, x is -1, and then I have that plus b. So 2 equals 3 plus b, and b is going to be -1. So there we go. I now know m and b, and my line will be y equals -3x minus 1. In general, when you're finding equations of lines in these kinds of situations, I always find it really helpful to just sort of split my task up into two ideas, right? Find m, find b. Those two tasks, and then put the information together to get your final answer. All right, let's check this one out. Once again, I'm going to graph the original given line. I'm going to graph the one we found, and hopefully they're going to look perpendicular. I could also verify that the point -1, 2 is on our line, just to double check that we did it right. All right, so let me get rid of these. The original given line was y equals 1/3 x plus 4. We think the perpendicular line is y equals -3x minus 1. Now, you might look at that and say, whoa, we must have done something wrong. Those don't look perpendicular at all. Here's the problem. My grid is not square. Notice that my scale is 0, 2, 4, 6 here, but 0, 10, 20 here. What I need to do to really see that they're perpendicular is make sure my scale is the same on both the x and y axis. So I'm going to hold down my shift key, and I'm going to go ahead, try and get this to the point. Okay, that's not too bad, right? You see how now the 0 to 2 on the x-axis is about the same as the 0 to 2 on the y-axis. So I have a square grid. Now if you look at the red line, the given one, and the blue line, ours, now they look a whole lot more perpendicular. They seem to meet at a right angle. So that looks pretty good. The other thing that I could double check is the point -1, 2 was supposed to be on my line. My line is the blue one. Let's check it out. X is -1, Y is 2. That's pretty good, right? There it is, -1, 2, right there in that blue line. So Desmos provides a really nice way to check some answers as well. You just have to make sure that you're thinking about your grid correctly so that you're seeing the geometric relationships that you want to see. All right, that brings us to the end of 2.4.